Okay, so thank you for coming back from break. I want to thank Leah and the SCN2A Foundation for inviting me, and I apologize for all the delays in sending you my information. So I'm Ted Cummins. I'm Indiana University faculty. The students in my department get Purdue University degrees, and we're located in Indianapolis, so officially people call us IUPUI. I'm going to tell you towards the end of the talk a little bit about the work we're doing with CBD. I'm going to, in the beginning of the talk, focus more on this concept of gain of function and loss of function mutations. And so the title says gating for occurrence, and that's going to be part of what I focus on, but I'm framing it in the context of this concept of gain of function and loss of function mutations. And we've been studying a lot of missense mutations in the lab. These are some of the SCN2A mutations that we've been studying, many of them corresponding to patients in Heather Olson's research cohort. We've also studied NAV 1.6 point mutations. And like a lot of the labs that do functional characterizations, we have a bias to want to, characterize the mutations and their changes as loss of function or gain of function. And I think that is actually problematic. And so one of the parents asked me earlier, is E430A gain of function? And I hemmed and hawed. Our data says it's gain of function, but I'm a little bit hesitant to say it's a gain of function mutation, because then the immediate assumption is it's early onset. There are point missense mutations that are clearly loss of function, at least from the electrophysiological analysis, they wipe out function. But some of the other mutations, it's a little harder to tell, and so I'm going to give you some examples from the literature and some examples from our own work. And so from the literature, we've heard about the Wolf paper from 2017 several times already, and it's a very nice paper. Their interpretation of their missense mutations is flawed. It's problematic. They characterize 4 disease mutations, 2 of them gain of function, 2 of them they characterize as loss of function, and they made this proposal that gain of function was early onset, loss of function mutations were late onset. So let's look at the data. This is their summarized data for their 4 disease mutations that they looked at that allowed them to make those fairly strong statements in the abstract of the paper. And the bottom 2 mutations are what they characterize as loss of function mutations. And they compared this data to the wild type data on the top. And so I'm going to zoom in on part of this table. The data on the voltage dependence of steady state inactivation and steady state activation. And if you look at this bottom mutation, P1622S, and you look at the voltage dependence of inactivation compared to wild type, those 2 numbers are clearly different. The voltage dependence of inactivation is much more negative for the mutant channel. That means inactivation occurs much more readily. That's clearly loss of function. And that's where they ended their discussion of this mutation. But if you look at the voltage dependence of activation, the mutant has a voltage dependence of activation that's 5.1 millivolts more negative. And 5 millivolts shifts are about my threshold for considering a change to be physiologically relevant. So I would say that looks like a gain of function. And if I run the statistics on their numbers, it's statistically significant. They don't classify it as a significant change, but I think it is. So I would say this mutation is gain of function and loss of function, a mixed phenotype, all right? So the other mutation, the G899S mutation, if you look at the voltage dependence of inactivation, there's no change there. That's okay. They didn't focus on that. But they looked at the voltage dependence of activation. There's a 2.2 millivolt shift in the voltage dependence of activation. It's more positive. They said that's loss of function. 2.2 millivolts is teeny. I'm not sure it's physiologically significant. If you run the statistics on those numbers, it's not statistically different from wild type. They put a star there, but I think that's an error. So their analysis of those mutants and their classification, in my opinion, is flawed. Yet that's driving some of the dogma in the field that gain of function, early onset, loss of function, late onset. We actually looked at the G899S mutant. Let's see. Yeah, it is a little slow at times. We looked at that mutation because it corresponded to one of the patients in Heather Olson's cohort, and we saw a hyperpolarizing shift in inactivation with that same mutant that in the Wolf paper had that 2.2 millivolt depolarizing shift. So we classified that one as gain of function. Error bars are big, we need to repeat that, but it's complicated. We also looked at G6959D. That mutant looked like clear gain of function, but the patient phenotype, absence seizures beginning at 16 months, doesn't fit with the dogma. It has a gain of function phenotype in the electrophysiological context, but it looks like late onset with absence seizures. So it's not fitting that simple classification. If you look at the Wolf supplemental table 1, there's a wealth of data in that paper. They have a lot of information on truncating mutations. 26 patients with truncating mutations, 14 reported no seizures. Of the 12 that reported having seizures, 11 had seizures with an age of onset that was 41.8 months. So one question is, what's the difference? Are there differences in truncating mutations where some patients get seizures and some don't? Are there genetic modifiers? But they have a much later age of onset. But I think we can all agree truncating mutations are loss of function. The most common missense mutation that's associated with late onset seizures is R853Q. Steve Petro's group looked at this mutation, concluded that biophysically it was loss of function. But in the Wolf paper, and that's cut off down here at the bottom, they reformatted a bit with the transfer. And I don't use apple to apple, so I don't know why I reformatted. They had 7 patients listed with age of onset for the R853Q. The average age of onset was 13 months. Those 2 cohorts, the truncation mutations with epilepsy and R853Q, are significantly different. So how can they both be simple loss of function? So we looked at the biophysical phenotype of R853Q, and we see more than just loss of function. So if we look at the peak sodium currents, they're smaller, but only about 50% smaller, not a drastic loss of function. But we see this anomalous gain of function, these gating pore currents. with this mutation. And we think those gating pore currents are driving some of the disease phenotype. So what are gating pore currents? So if you look at Bill Catterall's structure, beautiful structure, you can see very clearly the central pore of the sodium channel where sodium goes through. You can see the Mickey Mouse ears, the 4 of them that are the voltage sensors that move when voltage shifts and opens that inner pore. And if you look really close, you can say, well, there's a little bit of white space up here in that Mickey Mouse ear. Maybe ions could sneak through there. And you'd be almost right. Ions can almost sneak through these Mickey Mouse ears. And Bill and others have shown that if you put mutations into the voltage sensors, you can induce a leak through those Mickey Mouse ears, through the voltage sensor. You can induce a cationic leak through there. And some of these mutations that can induce a leak are disease mutations. So you don't just get your rapidly activating, rapidly inactivating pore current, you get a leak current that's induced by mutations in the voltage sensor. And this leak current is not blocked by TTX, so it's not associated with the pore. And we saw this type of leak in our HEK cells that are expressing R853Q channels. Steve Petro looked at it in his CHO cells and didn't see it. So we were not quite sure if what we were seeing is real. Gating pore currents, it's a very small leak. It's hard to see in mammalian cells. So we went to Steve Cannon's group, who has been looking at gating pore currents associated with hypokalemic periodic paralysis using xenopus oocytes, and said, can you look at our constructs and see if we are getting real gating pore currents? Xenopus oocytes are big. They can produce about 1,000 to 10,000 more channels than HEK cells. And what Steve and Fen saw were clear gating pore currents, validating that this disease mutant can produce gating pore currents. And if you look at the voltage dependence, these gating pore currents are occurring when the channels are closed near resting membrane potential, especially between -40 and -80, we see gating pore currents. And we think these are physiologically relevant. We're not 100% sure because they're small, but we think they're contributing to that difference in the phenotype. We're trying, boy, I really did reformat some of my slides. We're trying to pursue this using a zebrafish model, looking at the disease mutations and the human channel in a zebrafish, putting the disease mutation on top of a mutation that eliminates the pore conductance to see if a gating pore conductance is sufficient to alter the phenotype of a whole organism. We've looked at other weird currents besides gating pore currents. One of them being resurgent currents. Resurgent currents are also something that you don't normally hear about when you think about voltage-gated sodium channels, but they can contribute to disease mechanisms. We've seen resurgent currents with one of the other common SCN2A mutants, the R1882Q, increased persistent currents and increased resurgent currents. So we've heard about sodium currents transitioning the channel from the closed to the open configuration, allows the sodium to flux through the pore. The IFM inactivation gate inactivates the channels and shuts down the sodium flux. That's the typical dogma for voltage-gated sodium channels. Resurgent currents add a twist to that dogma. With resurgent currents, you not only get the influx of sodium during the rising phase of the action potential, but you can also get an aberrant resurgence of sodium current during the falling phase of the action potential. And this aberrant influx can contribute to hyperexcitability. So normally, sodium channels transition from closed to open to inactivated states. And if you do a protocol such as this, where you stimulate the channels and then put them into a moderate repolarization, you can see this opening of the channels, inactivation, and refractory currents. But under some conditions, for example, when the beta-4 subunit is present, one of the other beta subunits that we haven't heard about today, you get these resurgent currents that occur during the period when channels are normally refractory. You get this flux of sodium channels and sodium currents occurring when the channels shouldn't be active. And that flux can drive, not only help drive the upstroke of the action potential, but this resurgence, because it occurs on the downstroke of the action potential, can drive burst firing. And we think this contributes to some of the gain of function hyperexcitability. But that's hard to see under standard electrophysiological analyses. So this is another type of gain of function that's often missed when looking at the missense mutations. So again, this resurgent current, because of where it occurs on the downstroke of the action potential, can transition firing from single to multiple spikes. If you can dampen that gain of function, then we think you can reduce some of the hyperexcitability with mutations such as R1882Q. One of the things that reduces repetitive firing is cannabidiol. So we published back in 2017 that cannabidiol, 2016 I think, cannabidiol reduces excitability in striatal neurons, which have a fair bit of resurgent currents. That 1 micromolar CBD can significantly reduce action potential firing in striatal neurons. And at the time, we thought this was due to inhibition of resurgent currents in NAV 1.6 SCN2A. And indeed, cannabidiol can reduce resurgent currents in NAV 1.6 channels and NAV 1.6 mutant channels. Cannabidiol at 1 micromolar can reduce resurgent currents by about 60%. Is that physiologically relevant? Do patients see 1 micromolar concentrations of cannabidiol at their sodium channels? I'm not sure. But I think it could be contributing to the effect of cannabidiol or other cannabinoids. And at this concentration, we weren't seeing inhibition of peak NAV 1.6 currents. Well, the R1882Q mutation can also increase resurgent currents, can also lead to these currents that we think can induce repetitive firing. And so here you can see resurgent currents in wild type and mutant channels. The resurgent currents are bigger in the mutant channels. So we asked if cannabidiol could inhibit this aberrant current in NAV 1.2 channels. Here's a control resurgent current for NAV 1.2. Here's resurgent currents in the presence of 1 micromolar cannabidiol. And again, we're getting significant inhibition of the resurgent currents with cannabidiol, this time in NAV 1.2. We didn't see this inhibition with NAV 1.1. Peak sodium currents are not significantly reduced by 1 micromolar cannabidiol. But the resurgent currents, we get over 50% inhibition with 1 micromolar cannabidiol. So at least this hints to us that we might be able to develop cannabinoid-like compounds that can selectively inhibit resurgent currents, and I might be able to reduce repetitive firing without reducing initial action potential activity. And to us, this is a possible therapeutic strategy for reducing repetitive activity associated with sodium channel mutations. So SCN mutations that enhance activation and/or impair inactivation are typically associated with early onset seizure activity, but not always. There's gonna be outliers. Maybe because we haven't fully characterized the mutations, we might be missing something. That's always a possibility. Or maybe because of genetic modifiers in particular patients. Truncation mutations that induce loss of function are associated with late onset, but I don't think we understand why some of the patients develop seizures and some of the patients never do. Again, genetic modifiers are likely to be important. With missense mutations, I think it's a lot harder to tell. I think it's risky to characterize mutations based on a limited set of data as loss of function or gain of function. If you won't look at everything, you may be missing something like a gating pore current or a resurgent current or something we haven't thought about. Localization, induced changes, other things. Cannabidiol can inhibit aberrant sodium currents, particularly we think it can inhibit resurgent sodium currents. Again, 1 micromolar is a little high, but it's not super high. You might get enough of that lipophilic substance at the sodium channels that might be a realistic concentration in patients. There we go. Okay, so these are the people who did the work. These are my collaborators. Much of the work with cannabidiol was done by Emily Mason, but a fair number of people have helped contribute to this, and thank you.